So
Fantastic.
good morning.
I'll just introduce you, Anna, quickly.
All right,
Thanks
yes,
everybody
sure,
for joining us. We're joined today by Anna Preiss. Anna is a geoscientist with 13 years of experience in geology and related sciences. Anna holds an MSc in petroleum geoscience from the AAPG school in France and an MSc in geology from the University of Silesia in Poland. Currently, she's completing a PhD in salt tectonics as part of the Salt Dynamics group at Royal Holloway, University of London, where she conducts her research on the relationship between thin-skinned and thick-skinned salt tectonic processes in the southern North Sea Basin. In her studies, Anna develops methods to investigate structural trends at a regional scale and map fault coupling parameters. She also works as a geologist at Schlumberger, and as part of her job, Anna deals with seismic interpretation, modeling workflows, and in particular, complex 3D structural modeling. So without further ado, Anna, take it away.
Thank you very much. So I don't really need to introduce myself any further. So good morning, good afternoon, and good evening to everyone wherever you are in the world. Thank you all for joining the presentation and having me here today. I'm very honored to be presenting my work to you. And I figured I would start with a puzzle. Okay, I hope you like puzzles. If not, just please bear with me through this one. So I guess this figure is a no-brainer to all of you. Everybody knows this graphic by Mr. Hill from 1915, and Mr. Hill, who was a cartoonist, he just plays with our brains and asks us whether we see a young woman or an old lady. So of course, to this one there is no no straight answer, and apparently what you see has some psychological implications, right? But we're not here to discuss psychology, but geology. Then why am I even showing this picture? Because to me, in many cases, that is what really geologists have to deal with when interpreting seismic data around and below salt structures, because salt can sometimes really disfigure the seismic image. And you might think whether the fault goes this way or that way, or is the fault even there, or is it still strata or salt? So there are many ambiguities, and when almost nothing is clear, still an experienced structural geologist will figure out something. They will find some reasonable solution and solve the puzzle. But whether there's like hundreds and thousands of puzzles, and physically it may not be really possible to resolve all of them in a timely manner. So it may be a good idea to allow the computer brain to do some work for you. And that is at the core of my today's talk. So automating the fault interpretation process on a large seismic data set to allow regional fault correlation and structural trend analysis of faults and salt structures, right? So analyzing both. And all this is to define areas within the southern North Sea Basin, which are characterized by different types of fault coupling. And this study was done at Royal Holloway, University of London as part of my PhD project in the Salt Dynamics group. And I did it together with my fantastic supervisor, Professor Jürgen Adam, who unfortunately is not able to join today, but I need to give him a lot of credit for allowing me to develop my craziest ideas. And a part of the results that is related to the basement was already published in the Journal of Structural Geology in December last year. Okay, so now this is the area of our study, the southern North Sea, and it is a mature basin which has been explored since 1960s. So we have quite a good idea about its internal structure, as well as the location, shape, and type of salt structures. And my project in general is trying to understand how the salt is controlling the regional distribution of thin-skinned and thick-skinned salt tectonics. And in this particular study, we have focused on the role of salt in linkage between post-salt and pre-salt faults during a complex Mesozoic evolution of the basin. And the way we have decided to achieve this was through application of fault coupling parameters. So I'll get to it in a second. Just to identify sub-areas in the basin with different types of thin-skinned and thick-skinned coupling. Okay, so let's just briefly talk about what coupling is. So as you may know, depends on you know what's your area of interest, right? But you may know that salt tectonic processes are driven by two contrasting mechanisms. So this is either regional tectonic deformation of the basement, which is also called thick-skinned, or also basement involved. And it could also be gravity-driven deformation of the overburden on top of a regional salt layer, which is called thin-skinned. And if both mechanisms are present in the basin, then they interact. And this interaction is defined in terms of coupling, okay, which is also called linkage. So we can have complete coupling, like over here, or complete decoupling where faults are completely unlinked, or partial coupling where there's a mechanical and spatial relationship between the faults in the cover and the basement, but the faults are not like physically connected through the salt layer. And these little maps above the sections, they schematically show how coupling relationships can be identified in a map view. And analyzing those patterns on a regional scale can help us define areas with different types of coupling. So thanks to analog experiments, which were published by Jack and Calloway in year 2000, we know what and how controls the amount of coupling in the basin. And so let's take salt thickness as an example. So the salt in this figure is shown in black, okay, and its thickness increases from left to right. So you can observe that the higher the thickness of salt, the less coupled are the faults in the in the cover and the basement. Now there are at least 5 such controlling factors, and these include the displacement rate, thickness of overburden, the amount of displacement on the basement fault, and the cohesive strength of the overburden. And the combination of all of these factors decides on how strongly the faults are coupled in a particular setting. Okay, so once we have a better idea about what coupling is, let me tell you a bit more about the study itself. And I will start with some background information, then about the study area, and then move to the data set and methodology. Next, I'll elaborate a bit more on the regional and local results. And finally, I'll wrap up with a few conclusions and some future steps that are ongoing. So not really future, but current. Fine. So again, the area of our study lies in the southern North Sea, and it is offshore the UK and Netherlands. So I'm just looking at really this part, excluding Germany and Denmark over here. But it's a large area covered, covering a part of the UK and the Netherlands. And the basin itself, it lies within a larger salt basin, the southern Permian Basin, okay, which stretches from the UK in the west all the way to Poland and Lithuania in the east. And as I mentioned, I'm actually just conveniently seated at the eastern periphery of the southern Permian Basin right now, just outside of Warsaw in Poland. But coming back to the North Sea, the salt in the basin, whose limit is shown with this pink dashed line, is of upper Permian age. So this is Zechstein salt, and it has undergone basin-wide salt tectonic deformation, which is evident through presence of these concordant and discordant structures shown in blue and red. The underlying basement is of Caledonian and Etruscan age, and the post-salt sedimentary cover is of Mesozoic Cenozoic age. So the southern North Sea essentially consists of multiple subbasins, which were formed in a sequence of tectonic events. And these events are responsible for a present-day complex architecture of the basin. So maybe to better visualize this complexity, let us take a look at the regional cross-section. So this is a more or less 500-kilometer long section. I'm not really focusing on this part, but looking at the part that really falls inside the area of my study. Okay. But at a first glimpse, it becomes clear, okay, that the structure of the basin is quite complex. So those lower Mesozoic sediments, so Triassic and lower Jurassic over here, and here that were accumulated during the Triassic-Jurassic rifting, they are not present everywhere, and this is a result of the mid-Jurassic domal uplift and basin-wide erosion. And next came the upper Jurassic rifting, which was more localized, and it produced high offset faults in the area of the central graben, okay, and a thick syntectonic package of sediment, of upper Jurassic sediments here. And this rifting was followed by a relatively quiet period of Cretaceous thermal sag, and then in the late Cretaceous and Cenozoic, some of these Mesozoic basins, like the Salt Pit Basin over here or the Central Graben over here, they were inverted, and that also had a strong effect on the stratigraphic record. Now, as you can see, the basement structure also varies quite significantly across the basin, and different coupling styles can be observed in different areas. So we can find areas with mostly complete coupling, like in the Salt Pit Basin, as opposed to areas of mostly decoupled deformation, like in the Shelf and Cleaverbank High. There are also places where we can observe all types of coupling in one area, like in the Central Graben. So just a couple more words, or maybe not a couple, about the basement itself. So as you can see, the study area, which is shown with this blue polygon over here, it falls inside the brown area, which is the Avalonia Terrain. And Avalonia Terrain itself is believed to be made up of smaller terrains. Now, Avalonia collided into Laurentia and Baltica in Ordovician Silurian, and altogether they formed Gondwana and the Caledonian origin, naturally. And later in Devonian Carboniferous, Laurussia collided into Gondwana from the south and formed the Frescan origin. Now, why is this so important here? Because these events were actually responsible for the establishment of the tectonic grain in the area. And in fact, as a result of all this basement accretion, we can observe four main fault trends in the basement. So the main one is the northwest-southeast trend, but there's also more locally the perpendicular northeast-southwest, as well as west-east and north-south trends. And the last one, so the north-south trend, is mostly most present in the Central Graben area. So throughout Mesozoic and Cenozoic, those Caledonian and Frescan faults, they were subsequently reactivated in various tectonic regimes and regional stress orientations, which were not necessarily at right angles to the existing structures. And as a result, there was predominantly oblique sleep on the fault planes, and as a consequence, there's now a very high parallelism of the faults and very very large length to throw ratios. Okay, so these are elongated parallel faults with small throws. And in general, throughout the Mesozoic, Cenozoic, new faults were rarely formed, except for like link-ups between those elongated faults to accommodate the strike-slip movement. Okay, so from the basement, let's move to the salt, which lies above the Paleozoic basement. And as mentioned earlier, salt thickness can have a major effect on the amount of fault coupling. So this nice map by Strenko et al. From 2013 is showing the thickness of all Zechstein evaporite facies in the Permian basins in Europe. So that is the Southern Permian Basin over here, and a smaller Northern Permian Basin to the north of it. The extent of salt facies is shown with this not gray, sorry, but the green line over here. And inside our area of interest, which is this orange box, you can see that the thickness of salt is not really fully uniform, right? It's not really uniform. So relatively gradual changes can be observed outside of the main Graben system. So the central Graben area is over here, okay? But we can observe those more gradual changes outside of it, so more to the west and east of it, actually. But inside the Graben itself, most of the salt is trapped in tall salt walls and salt stocks. So this has an effect both on the coupling styles and the imaging of the basement below the salt. So talking about imaging of the basement, let's now look at the data set. So the data set used in this study is the mega survey data set, which was provided originally in full by PGS, Petroleum Geoservices, and now a part of it belongs to the Oil and Gas Authority. And it's composed of, at least the part that I used, is composed of 39 high-resolution 3D seismic surveys of a total area of over 61,000 square kilometers. So it's quite a huge area. Because that is approximately, the study area is shown with this blue polygon, just for reference. So it is about a quarter of the area of the UK and twice the size of Belgium. So you can imagine the size, right, of the data set. So on this really large data set, we ran a supra-regional attribute analysis to map pre-salt and post-salt faults. And naturally for this, we needed to consider some characteristics of the seismic data that may affect the results of attribute analysis, right? And these were mostly salt velocity pull-ups that really distort the geometries of pre-salt horizons. Then residual mist ice between merged surveys, any seismic artifacts, and also another artifact, which is the acquisition footprint at shallow depths. So just before I jump into methodology, just a quick reminder why we're doing this in the first place, right? So the aim was really to check on the regional scale what kind of fault coupling relationships are present across the southern North Sea, using the geometrical relationships that are nicely presented by Jackson and Hudek. That looks relatively simple in principle at the scale of an individual structure, but is much harder to evaluate fault coupling relationships for the entire basin. So I figured that I would compare the fault maps above and below the salt and see how these structures are correlated geometrically. But for that, I needed to produce the fault maps of the base and top of salt first. And I started with the more challenging horizon, which was the pre-salt basement. So why was it more challenging, right? What was the problem? The problem is salt. like always, and the way it affects the seismic reflectors beneath it, and around as well, right? So either below or in the area adjacent to the salt structure, there's always some problems with the seismic image. So the velocity of salt is significantly higher than of the surrounding rocks, right? Which results in salt velocity pull-ups on time sections, and this poor image around the salt structure. So keeping this in mind, I still made an attempt to map the pre-salt basement faults in the southern North Sea. But for that, really, I needed a method that would be relatively quick, automated, and reliable, of course, because of the size of the data set. Because just interpreting basement faults on 39 seismic surveys would probably take me many months. So you may remember that basement faults in the southern North Sea are highly elongated and parallel due to this subsequent reactivation. And this characteristic can be observed directly in a two-way time map of the base of salt horizon. Now, if we take a closer look at this red rectangle, at least two different and really evident fault systems can be spotted. So there's the northwest-southeast trend that actually is present in the entire area. And then we've got these northeast-southwest trending faults that are mostly just limited to this southeastern corner. And these faults running northeast-southwest. These are the so-called the Kaiser faults, which are responsible for high compartmentalization of the Rotligand reservoirs in this area. And if you look at this map in this particular area, the faults are so visible that you could just directly draw them in, at least the major ones, right? But not the entire basement can be mapped with this level of detail. If, for example, we take a look at this black rectangle right now, there's quite a bit of lineations visible in the map, like here or here. And we may think that this has something to do with faulting, and partly it does, but the strongest lineations are associated to salt velocity pull-ups. So these are not real structures, and unfortunately, these pull-ups obscure a part of what is going on with the basement structure below. So we see that mapping pre-salt faults is not that straightforward, and we would not only like to map the faults, but also quantify the basement trends and understand how they change across the study area. So how to do this, right? So we can either try to map them manually and approximate strike directions, but this probably not the best solution, as it may be problematic in areas with like low data quality. Well, one thing that it might be imprecise, but all methods are probably going to be imprecise with bad quality or worse quality, because the data itself is actually pretty good quality. But first of all, it's very time consuming. I mean, manual picking of faults this entire area. So no, we could also try to use seismic attributes. So there are attributes that allow to extract like fault patches from a seismic volume, and then just you obtain the statistics directly through some calculations. But unfortunately, the seismic data, especially below the salt, does not allow to obtain a very good continuity of faults for this type of extraction. And for such a large area, the fault patch dataset might be actually quite heavy. So there are also AI techniques, and they could definitely help map the faults. At the time when I was conducting the study, I didn't really have access to this type of method. So So I had to come up with something slightly different. And I'm sure that some of you would propose something drastically different, but let me tell you in a moment what I did. But you may also say here, but hold on, Anna. I mean, you do all this work probably for nothing, because there must be some regional published fault maps from this area. In the end, this is a very mature basin, so well recognized, etc. Right? So, yes, you would not be wrong. And indeed, there are fault maps of the pre-salt basement available in the literature, but they do not exactly meet the criteria that I would be looking for. And that is, first of all, to have a truly regional extent and cover the entire study area, right? So some are local rather than regional. Then, to show the level of detail that would allow a comprehensive trend analysis and defining geometrical relationships between or of individual fault pairs. And then to show everywhere a consistent mapping methodology. So some regional maps are a compilation of work of multiple authors, and thus multiple methodologies and multiple levels of detail. So to ensure consistency, I mapped the faults on my own. So this slide is just showing the methodology that I use. So let me just quickly tell you what I did. So for fault mapping, this workflow that we have established with Professor Adam, it combines seismic attribute analysis and raster tracing techniques. So essentially, the workflow consists of 3 main steps. Okay, that is edge detection using using the similarity attribute, but potentially it could be another coherency attribute. Then edge enhancement using untracking attribute, and finally fault mapping using automatic raster tracing. Okay, so just in simple words, I took these 39 3D seismic surveys I had, and I first computed similarity with them. And similarity is a semblance-based attribute, a semblance-based coherency attribute. And then I ran enhancement on it with untracking, which allowed obtaining a thin trace of a fault on an attribute map. And finally, I took this map and ran automatic image tracing on it in GIS software. So that was to trace the faults detected with the untracking attribute. So the advantage of doing this is that I got a data set that is composed of polylines that represent the traced faults, and they are already oriented and referenced in space. Okay. So finally, I took this data set and computed strikes and faults, or rather fault segments, and plotted those data on Rose diagrams. Now, just to give you an idea of the intermediate results and really what kind of limitations I had to deal with. So this is the similarity map, and it does show fault patterns very clearly in some areas, okay, like over here, for example, right? So we can directly see the faults as they are. But in some other areas where data quality is lower, so for example, over here onshore, the data quality onshore is lower, or where there are plenty of salt structures, you cannot resolve the faults very well underneath those, as I call them, shadows of salt structures, because these are effects related to salt velocity pull-ups. So it is quite difficult to determine the geometry of faults. But it is way easier later after the map is enhanced, and you can see that those black faults, they stand out quite clearly except for areas of lower data quality. So also below the salt structure. So, you know, this is a little bit not as well resolved as for example, in this area or onshore as well. It's the same situation. One disadvantage of this method, I mean, the one that I really find a disadvantage is that the attributes, and especially the untracking attribute, it picks up the borders of seismic surveys here on this data set, and it treats them as vertical events. They had to be filtered out, and because of this filtering, some of the data along the survey edges also was lost due to this filtering. Okay, so as you may remember, this map was then used in ArcGIS for fault tracing, and the result is this. It's a map of faults, or at least like polylines that represent the discontinuities picked up by the attributes. And this is a raw result of fault mapping process. Although it's not fully raw, because this map had some minor events removed. So I removed anything that I confirmed on the seismic sections that these were like seismic artifacts. Okay, so this is free of those obvious events that I'm sure of that would be seismic artifacts. So each of these red polylines represents a mapped fault. Okay, and again, this is spatially referenced, and it can be further analyzed statistically. But I can imagine that, you know, from your perspective, just looking at this on the screen, it is not very easy to look at such representation. But one important thing can be noticed immediately from the map, and this is the fact that these northwest southeast faults, northwest southeast, yes, they dominated the area. Okay, and this dominance is confirmed by the rose diagram over here, and you can see that the faults that actually fall between 110 to 160 degrees. So I'm taking a relatively wide angle, but it's still faults running more or less in this direction. So they make up approximately 51% of all faults. So it's a true dominance of this trend. And then, if you can, not sure if you can see it clearly, but there's a tiny peak over here, which corresponds to the faults that run in the northeast southwest direction. So all of these faults that we could see on the map before, they are also picked up by the attributes, and these are the Kaiser faults, which unfortunately partly fall in the area of this washout. So they are probably slightly underrepresented in the rose diagram. Okay, so let's just take a look at this map in a slightly different way, using colors. If we stick to this map in the bottom left corner, that is exactly the same map as I showed just a second ago, but just color coded by direction of faulting. So the colors in the map, they correspond to the colors in the rose diagram to the right side. And if you look closely, you will see that basement structure is really far from being homogeneous. Different colors dominate in different areas. This dominant northwest southeast trend clearly stands out in the majority of areas, but especially in the west and south. And the other trends are more important locally. So, for example, the navy blue faults over here, they correspond to, which correspond to that smaller peak, right? They have a strong representation around what is called the central offshore platform. And these are, again, these Kaiser faults. The north-south and east-west trends are mostly located in the northeastern part of the area. And now if you compare this map with a lower resolution map to the right, okay, that comes from the literature, you will see that those local trends are largely underrepresented. And this is also reflected in the Rose diagram over here, okay? So 70% of faults, 73% of faults fall in this angle range of 110 to 160 degrees. So so it is much more than what we actually mapped with with our attribute-based method. So when trend distribution is analyzed by Basin, we can see that the importance of the northwest-southeast trend decreases as we move towards the northeast, right? So it's much more evident over here, and then it changes quite significantly over here. So the western and southern basins, they show a very similar trend distribution, where the northwest-southeast trend actually accounts for approximately 60 degrees of all of the mapped faults in the area. But the area of the central Graben and the adjacent areas have a higher contribution of this north-south trend and other local trends. If you can see, there is one area just south of the Schilkrond High. It has a dominant east-west trend or west-east. So it's a little bit odd to have this area, which completely does not match to what is going on in subbasins around. And also subbasins that show a very similar trend distribution throughout their Mesozoic, Cenozoic history, they have gone through drastically different tectonic histories, in fact. So there's a hypothesis here that these areas with different trend distributions may represent smaller terrains which were accreted to Avalonia prior to the Caledonian collision. Okay, so I'm almost done with the basement, I promise. So this is a comparison of what was available in the literature and how this compares with our automatic methods. Okay, so you can see that the map in the bottom left corner, actually this one, where faults are interpreted manually, okay, using mostly 2D seismic, is actually quite similar to our result in general, of course, but it contains, say, less detail, especially in the direction perpendicular to the main structures. And this is partly a result of the orientation of the 2D lines that were used to interpret these faults over here. An advantage, but also somewhat a disadvantage of the automatic mapping is that it is free of interpreter bias, right? So it just takes the data and analyzes the fault directions on its own. Now, on the other hand, there are also some areas here, again, related to filtering, where some data is lost. So maybe some manual interpretation in this area could help. So just using the same type of methodology, we were able to map the faults not only at the base of Zechstein, right, but also above it, and we're also able to trace the salt structural trends. And all this information was then used to perform a qualitative and quantitative analysis of pre-salt and post-salt fault systems. Okay, so finally, now comes the part where we compared all of these three trends together. Okay, so just for your reference, the pre-salt faults are green, The post-salt faults are red or salmon, and the salt structures are blue. Okay, and the trend analysis for the entire data set, it shows a general good match between the faults above and below the salt, and a slightly skewed distribution of the salt structures, right? So it's a little bit skewed. But it doesn't really tell us much about where these different areas with different types of coupling are, right? So for this, we needed to analyze in detail the entire map of the overlay pre-salt and post-salt faults. So this map, okay? So what could we expect? Well, definitely not such simplified cases as in those tiny maps over here. But in areas of complete coupling, we could observe such nicely matching fault patterns, okay? While complete decoupling will show very little correlation between the fault systems. There are also intermediate cases where we have a mixture of coupling styles. Now, this is just at least fun for me. It's a fun slide to show how the interpretation was done in practice. Okay, so we could see that there are some areas where the faults are quite nicely correlated, like in this bottom right corner. Then they start diverging. There's a little bit of offset between them. They become less and less correlated. And finally, at some point, you get really no correlation between those fault patterns, right? So we could potentially put in some boundaries here. For example, over here, more or less, where we've got, where we stop seeing like such strong correlation between the faults, and then, well, I don't know, somewhere over here, maybe like this, where we stop seeing a lot of correlation anymore. Of course, there are places where you will still see a lot of correlation between the fault systems. So this study generalizes a bit the results, right? So you can't really, like, it's not the point here was not to analyze every structure, just delineate like boundaries between areas that have different coupling styles or different correlations. Okay, and also one other thing that can be analyzed here is, for example, the how the salt structures are correlated with, or the trend of salt structures is correlated with the basement faults. So there are areas where the trend of salt structures is similar to what is going on below it, but there are also some places where the trend of the salt structure, okay, is not coincident with the trends of faults below. So this way, based on the observed patterns and salt structural trends, I was able to define a few limits of deformation of the post-salt fill, post-salt basin fill inside the study area. So I defined an area of thick-skinned deformation and an area of thin-skinned deformation, and also I was additionally able to outline an area where salt structures are rotated away from the basement faults. And from these limits, we obtained three main areas of pre-salt and post-salt fault correlations. So there's area A, where correlation is strong, and we mostly have thick-skinned deformation. Then there is area C, so over here, and also a bit over here, where correlation is weaker, and thin-skinned deformation dominates in this area. And in between them, there's also area B, where both types of deformation in the cover can be observed. And additionally, area C prime is just a subset of area C, where we observe a significant rotation of salt structures with respect to the underlying faults. Okay, so now let's just take a quick look at these areas one by one. So area A is typically an area of dominant complete coupling with really no salt structures present, and this is due to either lack of salt, south of this line, or just very, say, relatively low thickness of salt. And faults above and below the salt follow the same dominant northwest-southeast direction. In area B, which is also partly the area of the central graben, we observe all types of correlation. Okay, all types of not correlation but coupling, and a much more spread distribution of fault trends. Okay, so there's no like very strong dominant trend really shown on the Rose diagram, and this is due to the presence of high offset faults that were utilized by the Upper Permian rifting in the area of the central graben, and they kind of like overprinted on the northwest-southeast basement trend. And also salt structures in this area, they seem to utilize this younger trend a little bit more. In area C, we observe partial to no coupling and a dominant but weaker trend as compared to area A. So it's the same northwest-southeast trend. And salt structures, when they are analyzed all together, they have a slightly spread out distribution. Okay, it's also a little bit skewed. And this is really a result of salt structure rotation in sub-area C. And here we observe almost solely complete decoupling. And you can observe the rotation on the Rose diagram over here. So it's rotated away from the basement faults. Okay, so as we move from area A to C and C prime, we observe a transition from highly correlated pre-salt and post-salt fault systems, where the formation is predominantly driven by basement tectonics, to less correlated fault systems and predominantly thin-skin tectonics. This also means moving from areas of complete coupling over here to complete decoupling in sub-area C. And additionally, an interesting phenomenon can be observed in this sub-area C prime, where salt structures are rotated away from the underlying basement faults. Okay, so let's take a closer look at it. And if you just look at the Rose diagram, where salt structures are shown in pink and the basement structures are shown in black, we can see that each of the diagrams has two modes. Okay, so one is the main one, and there is a weaker secondary one. And if you compare them for both faults and the salt, they appear rotated by approximately 30 degrees towards the north. And this could be interpreted as a pure shear deformation of the post-salt overburden, stretching in the north-south direction and shortening in the east-west direction. And it's a process driven by regional thin-skin tectonics. So to conclude, we have mapped pre-salt and post-salt faults using a combination of seismic attributes and raster tracing. And for the pre-salt basement, the trend analysis allowed identifying areas within the basin with similar or dissimilar fault trends, which may imply joint or detached origin, same or different origin, right? In terms of like pre-Caledonian accretion. Then we have come up with a robust method to perform regional analysis of fault coupling relationships by analyzing regional fault patterns and correlations between them. So 3 main areas from A to C were identified in the southern North Sea, where fault coupling changes from like complete coupling in A to no coupling in C and C prime. And some specific observations were made here in this area C prime. So as a rotation of salt structural trends may imply a gravity-driven transport of the post-salt overburden towards the basin center in a pure shear mode. And 3 factors seem to have a major control on the amount of coupling in the study area, and these are salt thickness and the amount and rate of the displacement of basement faults. So as the salt thickness increases from the margin towards the basin center, we can observe that the amount of coupling decreases. But in the area of the central graben, where the rift faults dominate, the basement fault displacement seems to be really taking over the role of the main controlling factor for the salt structure trajectories. So just a way forward from here, like I said, it's really ongoing. So I have done a quantitative analysis of basement fault displacement and salt thickness, and trying to analyze the relationships between them at a basin scale, and hoping to build a framework for such regional analysis in the future. And the results are really on the way. I just need to give me a little bit of time. So I'd just like to, thank the data providers, which is the Petroleum Geoservices and also the Oil and Gas Authority, as well as IHS Marking, Esri, and Schlumberger for providing the software packages that were used in the study. And also to the Institute of Geosciences at the University of São Paulo for making their software for structural geology analysis available under the open source license. So just a couple of references that were used in this study. And this concludes my talk. So thank you very much for your attention. And I open the floor to your questions.
Fantastic stuff, Anna. That was really, really cool. Really enjoyed it. We'll go through, we're getting close to 3 o'clock. Just wanted to check you're okay to answer a few questions for a bit.
Yes, no problem at all. I apologize for running over a little bit.
No, not at all.
That's me. I do that.
I've got a bit of a cough, so apologies if people hear me hacking up over the mic, but we'll start with the Q&A. I see people have been using both Q&A and the chat, so just get your questions in. Our first question comes from Sofiane Dejerzar. Did you highlight the Hercynian and Alpine orogeny in the study area, in the area of study?
Hold on, I have a map over here. What you mean for in the fault analysis, or because right now I've got I've got this map over here, and it's actually showing the areas that were inverted during the Alpine inversion of the of those Mesozoic basins. For the trend analysis, I wasn't really focusing on let's say the population of faults that would be related to a certain phase of deformation. but just analyzing the trends in general. So no, I didn't really focus on trying to split those, if that's what you meant, because I am not exactly sure how to answer the question.
No worries. I guess if Sophiane wants to clarify, please send us another little message. Our next question is from Wayne Camp, who's asking, what's the composition of the basement, of the pre-salt basement?
Yeah, so in most part there is the Rotliegend reservoir at the top, right? But there's so these are Permian. Sorry, this is the Permian sandstone, and below that there's Carboniferous and Devonian. And in some parts, but I'm not sure if actually in the study area over here, but in some parts the Devonian is, the erosion goes down to Devonian, so it's like there should be contact with the salt. But yeah, it's just it's most part the underlying sediments are the Rotliegend sandstones that make up the gas reservoirs in the southern North Sea.
Fantastic. And we've got another question from Sophiane asking if you used fractal analysis, and which distribution did the fault network follow? Was it log normal? Was it a power law distribution? If you looked into anything like that.
Okay, so the let's say I'm no, I didn't use fractal analysis. What I used was so actually I would have to look exactly in what the sorry, what was the method that was used for Rose diagram construction that was used in the software by the Institute of Geosciences from São Paulo. But what I can tell you is that I used a weight of the length of the different segments of the faults just to weigh the result of the distribution, right? Because the way I did it was that when I mapped the faults, the polylines were connected, right? So they had like very tortuous geometries in some areas. So I had to split them into small segments. And then I took all of these segments and analyzed them as being like kind of individual faults, but I used the length of each segment as a weight to make sure that I'm just not, comparing long segments with short segments, etc. So that's the principle that I use. But I would need to check and come back to you possibly on what is the exact method used by the software. So at this point, I just don't remember.
Awesome. We've got another question from Wayne Camp. Did you attempt to qualify the certainty of the attribute identified fault traces? It appears that the different faults strike in the northeast of the study area is also the area of thicker salt and therefore more uncertainty in the top basement pick.
Do you mean, hold on, over here, let me just jump into the right slide. Just looking at the right one. Okay, so you mean, for example, over here, that or the north-south trend. Okay, so again, I was looking at the seismic cross sections while running the analysis. So it's not maybe this is something that I didn't mention, but maybe to me it was so obvious because I was doing this analysis with the seismic sections analyzed along the way. I don't think it would be possible to really do this type of analysis without checking if the if the faults or the results that I got were actually, were actually there, if the faults were mapped with a certain level of certainty. But let's say I did not quantify it in any like, let's say, statistical way. I know that there are areas inside the basin, for example, the central Graben, or also towards onshore Netherlands and this whole southern part over here that have a lower level of certainty, also because of the data quality. And sometimes it's a little bit hard to figure out on your own, even looking at the seismic sections, whether the faults are where are the faults exactly. But in general, the at least for the basement faults, the match was pretty good. At the level of 50 milliseconds above the top of salt, that was more tricky. Well, I believe that some of the tiny faults that are mapped, they are probably mapped with a lower level of certainty. Again, this area over here in the central Graben, this is probably an area with that should be treated carefully, because again, I can imagine that the fault is running in a certain direction, and so does the software. I mean, the software analyzes the data, but if there is if there are salt velocity pull-ups and they are like very strong, the software can still think, okay, I've got a fault over here, but maybe it's not exactly in this position, or maybe the trajectory is a little bit different. Maybe it's not there. So I trust that in most part the method is working, and then I was able to check it. But there are some areas where it's really hard to assess the uncertainty here. So I'd say it's a bit uncertain. Just let me jump quickly into the where is it now? I can't see those. Yes, this map over here. So I say, up to here, I would imagine, that there's not much uncertainty on how the basement faults are mapped. But from this area on, except here, really, because this is there are some this is some pretty clear seismic in this area. I would be very careful with just saying, oh, this is for sure, this is a certain result. I say that there is such a structural complexity that probably the algorithms are not like doing. I mean, they're still doing a good job, but it's hard to assess how good they are.
Nice one. Yeah, I imagine the methodology section is quite extensive, having to sort of account for all these assumptions. We'll give some other people a chance to ask questions. We've got the next one is, are you still okay for questions?
Yeah,
okay,
sure, of course.
Our next one is from Phil Mollicone, who says, hi, Anna. For clarification, does salt thickness mean total Zechstein thickness? And he's also wondering, your study area does not include any of the Zechstein carbonate shelves to the west or to the northwest.
Okay, so yeah, so the thickness of the map that I was showing before, that is actually showing all of the Zechstein facies, right? So including the carbonates, etc. The only thing that was shown over there is really the let's say the extent of where the limit of salt is. But as we know, at the margin there is more. I mean, there's very little salt in comparison to other facies, and it changes towards the basin center where we've got mostly halite. As I was not really assessing the thickness of salt here as it is, and for the study, right? I'd say, I don't really have an answer here because I'm not using the salt thickness for this analysis. I will use it further in other studies to assess the depositional thickness of salt. So this is a little bit more tricky, and that would rather mean halite in general, because that is the mobile part that I'm interested in. Although, well, okay, maybe no. I should rephrase that, because at the edges or at the margins of the basin, I will still be looking at how the faults are not correlated, but how the coupling can be calculated using all of the Zechstein facies, just to see, because what I'm trying to do is just to evaluate the coupling, how it changes across the area. But maybe it would be a good idea to investigate it also in terms of just the mobile salt, and think of how the coupling is correlated with the thickness of the halite itself.
Nice one. Our next question is from Piotr from Warsaw. Interesting work, quite relevant to his ongoing study in the Polish basement and the role of basement faulting. His question is, the models you showed present linked and/or decoupled fault systems during extension, but the study area underwent some substantial, depending on where you are, inversion in the late Cretaceous and the Cenozoic. I know you mentioned at the start, have you considered this in your analysis? And then he goes on to say, some faults might have had earlier extensional history, some might have been formed solely during this compression that triggered the inversion. Would it be possible to distinguish these two types of faults?
Yeah, so I mean, from this type of analysis that I did, it's not really possible to distinguish them. I mean, there are faults in the basement, like not all faults in the basement. For example, in some areas they underwent inversion, and it's sometimes really hard to tell which ones did, and to what extent, right? Because the salt thickness in some areas is quite large. There's no way. I mean, I'm not saying there's no way, but let's say it's really hard to estimate. For example, how much the fault, moved up and down during during its tectonic history, because we have no reference at the top, right? So the fault is just kind of moving, and the salt accommodates all of the displacement. So no, I have not looked at that. And I think that actually it would be quite hard to do this for a regional study, also because to really understand which faults were inverted, you really need to look at each and every fault. Yeah, so that would be it. I just think it would be quite hard to really do this as a regional study, and if somebody comes up with a method to do it, that would be actually quite great.
Lovely. Our next question is from Mark Rowan, who says, "Hi Anna, excellent job."
Hi Mark.
You proposed a possible east-west shortening at the end of your talk due to gravitational movement. What would have been the timing of this gravitational event?
Yeah, so I think one of the things is that the basement, because you probably know very well the area, Mark. There were multiple, events of basement tilting, right, and inversion, etc. And so this area was uplifted and bent towards the west or southwest during the uplift of the gravel shoulder in the Upper Jurassic. At the same time, there was another tilt that was caused by the inversion of let's say the salt pit basin, So there was like multiple events. I have not really like analyzed this in detail. I think that actually Chris Brennan, who is one of the other PhDs working with me on this data set, might give you a better answer, because he analyzes the timing of the events in the basin. But you know, I believe that it's like an overall kind of result of what was going on at different stages of the basin evolution. But maybe you can correct me on this and you know, and give me a better solution to that. But you know, I can observe clearly that there's a stretching in this north-south direction because of this, you know, rotation of the salt structure. So it would be kind of sorry, where's my mouse? So it would be mostly, you know, this area where we've got, you know, this uplift of the salt pit basin over here and the uplift of the shoulder over here, and everything seems to be just, you know, squeezed in from both sides over here and stretching towards the basin center in this area. So I hope that that answers the question, and you know, maybe you know, you have some comments as well, so you know, let me know.
Thanks, Anna. Awesome. It's Gabi here now. I'll just continue with the questions. Are you okay to answer a few more questions?
Yes, Gabi, but I can hear you not very well. If you could...
Can you hear me a bit better now?
I think a bit better, yes.
Okay.
Is it better now?
Yes, it is better, yes.
Okay. Yeah, so next question from Thorsten Hansen, and he says, great talk, Anna, thank you. Really interesting methodology with an impressive area coverage. Question, did you perform any QC of the automated fault interpretations in seismic sections with manual interpretations for comparison? And if not, how robust do you feel your method really is for seismic data of varying quality?
Okay, so I mean, that was partly touched on before, but let me just jump into this slide for a second. In terms of comparisons, you know, how it compares with the manual interpretation, I did not really do a manual fault interpretation in this area. Maybe some, you know, maybe on a very small area, but I can see how it compares with, you know, with the manual interpretation done by other authors. And to me, the trends that were picked up and the changes of trend as well, they seem quite reliable. So of course, again, this is an automated method, and it can pick up things that you would not like it to pick up. But this was developed by myself and Professor Adam for a large regional analysis, when you really have limited time to to pick all of the faults in the area, because it would not be possible to do that comparison during the time that I have for my PhD, trying to pick all of the faults in the entire data set. So, like, from what I can see, how the algorithm is dealing with it, with the faults in comparison with the manual interpretation that I had on hand, I think it's doing a pretty good job. But again, just answering your next question, I'd say of course, the better the data quality, the more reliable the result will be. So I would probably not try to use it on a data set where we cannot anywhere confirm that what you're mapping is is what's actually there. And just as a comment for, for this study, it's not that I ran the attributes once and got a good result. Actually, that took quite a bit of trials to see how the faults are mapped, and looking at the seismic sections as well to confirm that the faults are actually there where they should be, or that it's not picking up some, for example, some layering, right? Some bedding. For example, at the early stages where these coherency attributes are computed. So it really does take a couple trials, and the overall result is a result of some multiple trials. And again, the data set, the data quality in the study area that I had was actually very good in the majority of the area. And there are just some parts that, it's really hard to resolve what is going on actually, and it's hard to check whether the attributes are picking up the faults where they should be picking them up.
Mm-hmm. Yeah.
But sorry, if I can just add one more thing to it. One of the checks that I did as well was that I took on a smaller data set where we had some salt structures. Okay, so I ran the same analysis, and what I did is I checked the trends for the entire area, and also the trends beneath the salt structures and beneath the depot centers between them. Okay, just to see how the overall trends are corresponding, right? So to see whether the salt structures are actually affecting much the trends in the basement as compared to as compared to the overall data set or areas around. And what I got is those rows diagrams that look quite similar, meaning that even though in some parts the salt structures probably obscure the basement, the reflector, right, to such an extent that the attribute is not able to pick up much, because there is some diap here over here. For example, so in some areas it might be quite hard, quite tricky, but at the same time, the trends are kept, or they are the same, or more or less the same as for the areas where there is no salt structure, right? So I would say it can be trusted. At least in in the area of my study. Hello?
We cannot hear you, Gabby.
Hello?
In the meanwhile, Nawaz, I have a question.
Yes.
For the stereo nets, what software do you use? They're quite.
Yes. So sorry. Go ahead.
Yeah, I said they're quite impressive. I just wanted to know what software do you use for the stereo net?
Yeah. So for the stereo nets, I used Open Stereo. It's called. So
Okay.
so the software comes from the Institute of Geosciences of the University of São Paulo. So this is an open source software, and obviously the rows diagrams that I'm showing here, they are colored by myself and everything. But you know, it's a very easy to use software that allows not only to analyze the strike, but it also has some other capabilities. So you know, I think it's you know, the University of Sao Paulo should be yeah, should be given some some credit as well, because they, you know, they provided it as open source, and very grateful for it.
Can you hear me again?
Yes, we can hear you.
Yes, we can hear you.
Okay, sorry about that. Yes, so shall we proceed to the next question? It's from Ian Watson. He asks, since you've identified salt thickness and fault displacement as two key factors, have you overlain the salt isochord with your domain? And have you filtered your faults by the amount of offset?
I'm sorry, could you repeat the question? Because I didn't hear the whole thing, I think.
Okay. Since you've identified salt thickness and fault displacement as two key factors, have you overlain the salt isochord with your domains? And have you filtered your faults by the amount of offset?
No, I have not. I have not filtered the. So okay, so the no. In this study, I did not look at the offset of faults. This will actually come later, because you know, I was trying to find a method to look at to say estimate or approximate the offset of all of the faults in the basin. But for this one, no. I just looked only at the trends of faults. So not really looking into how you know, the how did not say that this is more of a geometrical analysis, without really looking into numbers, without you know, quantifying the coupling quantitatively, right? So that was like a qualitative analysis, and now the next step really for this study is and has been to analyze it quantitatively. Yeah, so at this point I was not doing this.
All right, thank you.
I guess just a quick question for myself then, with regards to, because it's quite interesting they're thinking about estimating throw. Sorry, this is Connor here, by the way, butting in. Because I guess your map of faults, the attribute map that you produce with the faults, essentially is a map of heave, and you've created heave polygons for each of your faults. If you think of slip, throw would be the vertical displacement,
Yes,
and heave would be the lateral displacement. So if you could work out a way to work out how thick, I guess, how many pixels or how many points thick each fault is, you could then come up with a very rough estimate of how to calculate the throw on the faults or the slip on the faults, potentially.
Yeah, I mean, I think it would be possible if I only used similarity, for example, or any other coherency attribute, because they actually should show the width of the fault. But when I run enhancement on it and use untracking, what untracking does, it reduces the, let's say, the thickness of the zone, because it tries to pick the you know, kind of the fault, no, not pick the fault, but just there's a part of the what the algorithm does, it's called narrowing, so it narrows down the zone. Okay, so you are not able really from the final map of faults to tell what the heave is, because it just shows you the trace of the fault, or you know, any discontinuity. So unfortunately, this doesn't work this way. It would be fantastic,
a lot easier.
But yes, exactly. But you know, I have I found another way to like approximate the throw of faults, and this is not using the attributes, but you have to wait for results. So I can you know, make sure that that it works properly. And again, like with all of these regional studies that have to go into detail, but at a at a large scale, there's always going to be quite a lot of uncertainty. So also for the methods that I'm developing to analyze or to quantify the throw on faults and the coupling, but quantitatively, right? It's at the regional scale it works, but always there's quite a lot of QC that needs to go into it, and at a certain level of trust that can be applied.
Cool, thank you.
Thanks, Anna. There's a question from Gonzalo Calvo. In the whole stream map you showed, there's an area towards the left, those in fault area, where echelon sigmoidal faults appear. Is there a strike slip deformation phase considered in the structural model?
Yeah, so there's definitely strike slip deformation. Sorry, I'm not sure which. Hold on, is there anything? So you probably also mean this area over here, right? There are some major strike slip faults running through this area, and anyway through the southern North Sea in general. So a lot of the movement on the faults was actually like oblique slip, and these these are present, and these are also picked up and mapped. But again, I did not make an attempt to show like different populations of faults or to distinguish between them in terms of the mechanisms of deformation. So they're there together with all of the faults that were also, for example, inverted, and also all of the extensional structures. But from this in this study, I did not distinguish between them, and I did not, with the method that I used, actually need to probably like really go into detail in each area and try to see which fault is which. So for this large data set, probably this would be a topic for another PhD.
Mm-hmm. Definitely, yeah. So there's a question from Alan Hollingsworth. I have experienced issues with producing attribute maps with the PGS mega survey, owing to striations that are probably linked to legacy survey acquisition lines, creating linear artifacts on mapped horizons. I was interested to hear more about your filtering of the seismic volume to remove edge effects and etc., and whether you experienced similar issues, particularly with post-salt horizons.
Yes. So yes, thank you for this question. Actually, I have a small slide over here as well. Yes, there's quite a bit of things that are present in the mega survey data set, and even for the horizons that have like really nice faults, you can have some areas where you've got I don't know, acquisition footprint or some lines that come from like merging the original seismic surveys, and so the filtering that I did was that was done at the stage of computation of the untracking, because in untracking you are able to filter out certain dips and azimuths. Well, unfortunately, all the filtering is going to have some implications also for like real events. So what I did is I filtered out all of the events that were dipping, I think 88 to 90 degrees, because that was enough to filter out, but running in a certain direction, right? So these were, so in the direction of the inlines and crosslines, okay? Because This allowed me to remove all of these vertical events along the edges of the seismic surveys. And I think that was quite a long time ago when I did that, but I think I also ran like a 1 degree filtering. I think so, but I think I put it in my paper actually, so I can you know, if you write me an email, I can send you the paper. I also applied some additional filtering at a very short like angle window for all, you know, for all of the area in all directions, just to make sure that I can remove, for example, the acquisition footprint, and you know, those like lines that come from like mismatch, and so those misties between the different seismic surveys. And that worked quite well. Sometimes it's not possible to remove everything, and sometimes it's you know, it's hard to tell whether, you know, the thing that is left. So, for example, this line over here, that might be, you know, that is probably acquisition footprint as well. If maybe it's not like mixed with some structure. So sometimes you can remove everything. Sometimes it doesn't fully work. So it's just, you know, a matter of really defining the parameters right, finding the right values, not to remove any geological information, but still get rid of the artifacts. But again, if in case where, you know, where there is where there are obvious lineations in the data, for example, when I then turn it into a polyline data set, I can remove these polylines directly. So I preferred not to really go too far with filtering out the information, just to a point where I don't have to really pick everything by hand and remove it later, because I prefer to leave the geological information, not get rid of it and just you know, do some additional corrections on the data set. But again, for the basement, it was not necessary. That was more for the horizons that were shallower. So also in some areas above the salt, that was necessary to remove some lines from acquisition footprint, for example.
Mhm. Excellent, Anna. There's still many more questions in the chat. Are you still happy to keep answering them live, or should we email those questions to you?
I think I can still have about 10 minutes, if that's okay.
Yes, absolutely. Yes, thank you.
But I'll be happy to answer all the questions by email. No problem.
Okay, excellent. Thanks very much. There's a bit of related to this, again from Gonzalo Calvo, about the oblique rectangular grid blank in the automatic fault map. I think this is the edges of the surveys you mentioned during your talk, and he asked if does this affect the overall analysis?
Could you read the first part of the question once again, please? Because I didn't get which part.
He says there is a clear oblique rectangular grid blank in the automatic fault map result.
Ah, yes.
Yeah,
yes.
I think someone even mentioned the chat there. They are called the boundaries of the PGS tiles from the boundary of the surveys. Yes,
that's correct. These are exactly what was mentioned. So these are the edges of the individual reprocessed surveys from PGS. So I did not find a better way really to remove those effects, because again, they were picked up by the attribute and treated as faults. So unfortunately, this needed to be filtered out together with some geological information.
Excellent. So in the chat we have from Ian de Jones Anderson. What was the processing time to run a similarity attribute for the PGS mega merge? Did you run this for the entire cube or just in a small interval around the basalt?
I did not run it for the entire cube, but it wasn't. Okay, so I limited it only slightly from the bottom, where I didn't really need to go that deep into the basement. Let's say it was maybe 80% of the data of those 39 surveys. And if I remember correctly, running the attribute on it took maybe 6 hours. But to be honest, I did not have a very powerful machine. So I think it's still a pretty good time. And then the same thing with the other attributes, or with untracking. It also took approximately this amount of time. So actually, I'm happy with the time of it, because it's really a huge data set, and obtaining all of this is such a short time. Kind of, but I think 6 hours is very reasonable. That's quite a success. But of course, I'm talking about, like, if you know exactly what parameters to choose, and etc., and how to how to define all of the just parameters for each of the attributes. Then it's easy peasy, but it's always testing of what's going to work best. So I used for the similarity, I used quite a long time window. And the reason for that was that because when I ran it with a long window, so it was like extremely long, so it was 240 milliseconds, okay? So I ran it with this time window, because then I could get a better, like, horizontal definition of the faults, because I was not really interested in what is going on vertically, just to map the faults on the basement. So 240, 110, and even less, just depending on what works best. Using a very high window can also produce some artifacts here and there. So it just also depended on the area. But overall, I used quite a large window just to get a better horizontal definition of the faults.
Mm-hmm. Perfect. One more question from Ian. He asks, I think in some areas, rafting of the Platte and Dolomite also interferes with the amplitude of the basalt reflector. Did you recognize this in your coherence maps?
No. That's I did not consider this, to be honest.
Mm-hmm. And another question from Tom Kefferky. An issue here is that diapirs are, because there was a new mess. Okay. An issue here is that diapirs are likely to have the purest imaging beneath them, thus obscuring faulting beneath them. This could mean you have a self-reinforcing model under extreme halokinesis.
Sorry, I did not understand the question.
Okay, yeah, I didn't either, but let me try again to read it. Issue here is that diapirs are likely to have the poorest imaging beneath them, thus obscuring faulting beneath the diapirs. Could this mean you have a self-reinforcing model under extreme halokinesis?
I'm not sure. I'm actually not sure if I understand the question. Would it be okay if the author of the question contacted me directly by email?
Yes, yes, definitely. Tom, please send us later by email. You can send to our AAPG email or an email directly if you prefer.
Thank you.
Okay, then one more from Huzaifa El Bushra. And besides structure effect of salt movement, is there an impact of the salt for source maturity, if any?
Yeah, well, I mean, I did not really think about it much when doing the structural study. No, but I mean, I mean, always when the salt is moving, there's definitely some effect on the strata that is around it, right? So depending on where the salt moves, I mean, when there's, for example, rotation of structure, so the salt will try to migrate somewhere out of the place where it is and move laterally to together with the with the strata. So I mean, it's not that the salt is moving along; it's the strata that is on top of salt that is moving together with the salt and potentially because of the rotation, some of the strata which would also find itself in a different position, right? Because there is rotation of the fault blocks and well, I guess that's that would also affect might also affect the maturity when it gets buried deeper at some point in some area, etc. But that's I did not analyze this in my study. But thank you, Zaifa, for the question.
Yeah, excellent. And I think we've gone through all the questions now, and
okay.
Those 10 minutes are up. And it was a brilliant presentation. Thank you very much. And hope everyone enjoyed your talk. I'm sure they did. And yeah, excellent. Thank you.
No, thank you very much for the opportunity to for me to give a talk at this webinar series. It was a great pleasure and a great honor, really. So thank you very much, and I hope that I can give another talk at some later stage when I'm done with the rest of my studies.
Yeah, definitely. We are planning the season 5 for this for autumn, and yeah, it would be great.
Okay,
Thanks
you.
a lot.
Thank you very much.
Have a great day or evening, everyone.
Thank you.
Thank you.
Bye-bye.